The physical universe relies on repeating rhythms. In physics, any movement that repeats itself over equal intervals of time falls under the broad category of periodic motion. The rotation of our planet is a macro-scale example. It completes a cycle, returns to its starting state, and begins again on a predictable schedule. Oscillatory motion is a specific subset of this behavior. A moving object qualifies as oscillating if it travels back and forth across a central equilibrium point, like the vibrating prongs of a tuning fork. This creates a rigid rule for dynamic systems. Every oscillatory motion is periodic because it repeats, but not every periodic motion is oscillating. Take orbital mechanics. The moons of Saturn follow periodic, reliable paths, but they travel in continuous loops. Because they never sweep back and forth through a single central point, an orbit is periodic but not oscillatory. When an object does oscillate and its displacement from the center varies over time in a smooth, sinusoidal wave, it achieves the most mathematically refined state of movement, simple harmonic motion. While we can analyze physical systems like a bouncing spring or a swinging pendulum in isolation, mapping their movement to a circle provides the mathematical framework necessary to derive their governing equations. The back-and-forth rhythm of simple harmonic motion corresponds exactly to the one-dimensional shadow of uniform circular motion. Look closely at this 2D geometry. A single point travels along the perimeter of a circle at a constant speed, locked at a fixed radius, which we label A. If we drop a perpendicular line from that orbiting point straight down to a flat horizontal axis, we create a projection. As the point travels its 2D circular path, its one-dimensional shadow point sweeps left and right across the line. Because the shadow is bound by the circle's edges, the maximum distance the shadow travels from the center perfectly matches the circle's radius. In oscillation, that maximum displacement is the amplitude. The point rotates around the circle at a specific angular frequency, represented by the Greek letter omega. This rotational speed is simply 2 pi radians divided by the time it takes to complete one full cycle. If we pull this horizontal axis forward through time, tracking the shadow's exact position, the projection draws a continuous cosine wave. The exact shape of the wave depends on where the point begins on the circle at time 0. That initial starting angle is known as the phase constant, denoted by phi. The sinusoidal equation for displacement, x equals a times cosine of omega t plus phi, is the literal geometric coordinate of a rotating circle projected onto a single line. Knowing where an object is located is only the first step. To understand the physics, we have to measure how fast it moves by tracking its velocity, which is the rate of change of its position over time. These 3 synchronized graphs track position, velocity, and acceleration. When the object reaches maximum displacement at the outer edge of its swing, it must stop to reverse direction. Velocity drops to 0. But as it crosses the central mean position, it reaches maximum speed. Because of this timing, the velocity curve trails the position curve by exactly a quarter cycle, creating a permanent 90-degree phase shift. Now, watch the acceleration curve at the bottom. Acceleration reaches its maximum magnitude at the extreme outer edges of the swing and drops to 0 at the center point. This creates a 180-degree phase shift. The acceleration wave mirrors the displacement wave. When the object is pushed to the far right, it accelerates to the far left. This proves the master kinematic constraint of simple harmonic motion. Acceleration is always directly proportional and exactly opposed to displacement. We can apply these mathematical constraints to a physical horizontal spring mass system. As the block is displaced to distance x, the spring exerts a restoring force in the opposite direction. By setting the physical force of Hooke's law, F equals negative kx, equal to Newton's second law, we find that acceleration equals negative k divided by m times x. This matches the exact kinematic constraint we found in our geometric model. This proves the restoring force of a spring provides the physical requirements to sustain simple harmonic motion. By comparing these 2 equations, we derive the time period for a spring mass system. T equals 2 pi times the square root of mass divided by the spring constant. Notice that the variable for amplitude is missing from this equation. Because the spring's restoring force scales linearly with distance, it physically pulls harder the further it is stretched. Increasing the amplitude does not change the time it takes to complete a cycle. A simple pendulum is a different physical mechanism, driven by gravity rather than the internal elasticity of a spring. Its period formula relies on its length and the acceleration due to gravity. For a simple pendulum, the mass of the bob is irrelevant to the time period. But as the measured arc in this diagram shows, there is a physical caveat. Unlike a spring, the gravitational restoring force of a pendulum is not perfectly linear. To model a pendulum as simple harmonic motion, we must use the small angle approximation. Only at angles under 10 degrees does the sine of the angle roughly equal the angle itself, ensuring restoring force is proportional to displacement. Whether the driver is spring elasticity or gravity, a system must generate a proportional restoring force to satisfy the mathematical requirements of simple harmonic motion. Beyond the forces and phase shifts, oscillation involves a continuous trade-off of mechanical energy. Watch the bar graph on this moving mass. At maximum displacement, kinetic energy drops to zero and potential energy peaks. Passing the center equilibrium, potential energy becomes entirely kinetic. The total mechanical energy is their constant sum, equaling 1/2 k times the amplitude squared. This total remains constant throughout the cycle. In the absence of friction or damping, the energy is independent of both time and the object's specific position. Simple harmonic motion demonstrates how energy is conserved through a continuous transfer between kinetic and potential states. By mapping these physical forces to circular geometry, we can predict the behavior of both mechanical springs and gravitational pendulums using a single mathematical framework.